Hello again. We have Andy here today. He's a PhD student at Michael University and Mila, focusing on temporal graph learning. He's interested in representation learning on temporal graphs, anomaly detection, and graph representation learning. He was the organizer chair for the temporal graph learning workshop at NeurIPS 2022. His previous research includes change point detection on temporal graphs, COVID-19 disease modeling with temporal context graphs, and the link prediction on temporal graphs. So yeah, we are happy to have him presenting this paper.
Thanks. So thank you everyone for coming to my talk today. I will be talking about my my PKDD paper, recently presented at PKDD. Just recently, like get over the jet lag. But I will be sharing the link to the slides in the chat, so you can follow on the slides as well. And I'll be sharing my screen. And yeah, let's get started. And then feel free to interrupt me for any questions and so on. And Pharma, can you let people in, like if you see? Yeah.
Yes, sure. Actually, I don't see the, upcoming guest, but I will.
Oh yeah. I think everybody is admitted right now, but I think you should see a notification. But anyways, I will handle it on my end too.
Thank you.
Yeah. All right. Yeah. So hello everyone. I guess just to reiterate, I'll be presenting like a sequence of work that I've done in the past. So this is like the main, like one of the main topics in my PhD, and then I've been working on change point detection for a few years now. So yeah, so like for today's talk, what we will do is I will first talk about an introduction to anomaly detection on graphs and temporal graphs. And then I will first talk about my previous work at KDD 2020, which is LAD. And then I will talk about my most recent work at PKDD. Okay. And feel free to ask any questions. Okay, so first I will talk about just to get started with it, like with the basics. So we are all on the same page. So so how do we define an anomaly? So an anomaly is an observation that are very different from other observations, such that you would suspect that it was generated by a different mechanism. So this is one of the first definition of anomaly, defined by Douglas Hawkins in the 1980s. And in practice, this definition of anomaly can depend on the types of interest and the nature of the network. And also this is technically not very well defined, and this is usually strictly a unsupervised task, because the assumption will be that you do not know what type of anomaly you will be encountering. So so the goal here is just to detect the outliers. So as you can see from the plot on the right, this is a very simple example of anomalies. You can see the outlier O1 and O2. They are outside of the clusters, as well as O3. And just one point as well, the anomalies don't necessarily follow the same pattern as well. So you can have different anomalies as well. Okay, so now as an example to get started, here is an example graph. And so let's take a few seconds to see if you can find where do you think are the anomalous users or the node on the graph that are different from the other users. I think you should be able to see it. Their behavior is different from the others. So the answer is these two users. So one, because they have different attributes, and the other one's because it's connected with a different community. So these are like two example anomalies from a past paper. And then in terms of anomaly detection on dynamic graphs or temporal graphs, we generally have 4 types of anomaly. So we have the node anomalies, we have the edge level anomalies. We can also have like anomalous subgraphs. And then for the focus of the talk today, we'll be talking about anomalous snapshots, or the entire graph snapshot of a like in a particular time in temporal graph. Okay, so I will get started on the first paper for today, which is titled Laplacian change point detection for dynamic graphs. This is a joint work with Yasmin as well as my supervisors Guillaume and Rehane. And yeah, just as very quick background, I think everybody here is like familiar with dynamic graphs. And here I show one example of the co-authorship network on the like on the MAG. And here just one simple illustration. In temporal graphs, the edges and the connections can change, as well as the number of nodes and so on. And then a few more examples. You can also have a dynamic graph that are like between like politicians. So like in this cases, the Canadian bill voting network, where nodes are the member of parliament, and then if they like they all vote yes on a bill, then they will be connected to each other. And then we also have the standard social network, which is like users and messages. Okay, so now we will first start by defining the change point detection task on dynamic graphs. So first, what do we mean by change point? So the change point is the point in time where the underlying graph generative model changes. So and then one very related type of anomaly is called events. So the events are one-time change in the graph structure, and the change points are permanent change in your generative process of the graph. So as seen in the visualization on the left, so when you have a generative model of type A, and then after events, you go back to the same type of generative model, while for the change points, you will change your parameter of the graph generative model. So the assumption here is that the dynamic graph is generated by this hidden graph generative process, and that's like what we try to model here. And the example applications for change point detection includes traffic accident identification, the changes in political environment, as well as events in social network. So how do we actually detect these changes on temporal graphs without injecting bias on specific set of structural changes or nodes and so on? So here we are trying to model the change in the entire generative process of the graph. So if you have one particular node that is anomaly, that might affect the local changes, but it might not be a global change. So in order to do that, we propose Laplacian anomaly detection, or simply called LAD. And here's one example about how LAD works in practice. So we have the Canadian bill voting network that we see from before, where the nodes are the MPs in Canada, and the edges are the co-voting pattern between the MPs. And here we can see that the anomaly that we detected are the graph snapshot at 2013, where we're actually in this year, Justin Trudeau is elected as the Liberal Party leader in Canada. So we can see a lot of cross-community edges, in particular for this visualization as well. And that will constitute one example of the global graph changes, or the change in the graph distribution. Okay, so in terms of the key ingredients of LAD, so first we treat the temporal graph as a sequence of graph snapshots. Here we're working with discrete time dynamic graph, which is different from some of the previous talks that we look at. And in particular, you want to summarize each of the graph snapshot in time, because comparing the graphs themselves, like two matrices that can sometimes even be different size, can be very difficult. So we want to first embed each graph into a graph embedding. And here in this work, we propose to use the Laplacian eigenvalues, which is motivated by spectral graph theory. And I will talk about that like in more detail. And then once you obtain these embeddings of the graph, or we call it the signature vectors, then you want to compare these signature vectors over time and see how these vectors are changing, right? So how you would do that is that you would put these vectors into sliding windows, and then you will compute the normal behavior out of this sliding window. So let's say k steps in the past, and then you will compare that with the actual vector that you have currently. And then lastly, we compute a similarity score, which is designed to be the cosine similarity between the signature vectors once you have computed them. And the cosine similarity has a very nice property of between 0 and 1. So this will be bounded as well. So as the flowchart of the methodology of LAT, first we take the graph Laplacians, and then you can extract the singular values from the graph Laplacians. And then you will look at the top k singular values. And then if you are an undirected network, then this would also be the eigenvalues of the Laplacian. So you will look at the top k singular values. So you have a k-dimensional embedding vector for each of the graph. And then you would take your current vector at time t, and then you will look at k steps in the past. Let's use like a different number like s, and then that will have the sliding windows. In this work, we want to model both the events and change points. So for the events, they are more abrupt changes. So we have a short-term window. And then for the long-term changes, we have like a slightly longer window, which then models the change points. So you want to take like two sliding window, one is short-term and one is long-term. And then you will compute the similarity score between your current signature vector and the principal eigenvector of the vectors that you stacked into this sliding window. And that gives you the final anomaly score. Okay, so here to motivate a little bit more on why we choose to use the Laplacian eigenvalues to summarize the graph snapshots. The first thing is that because they form a spectral signature of the graph. So the eigenvalues would actually reflect the graph structure, connectivity, and geometry. So for example, a well-known theorem is that the number of connected components of the graph is equal to the number of zero eigenvalues that you have in the Laplacian spectrum. And the eigenvalues are also no permutation invariant. So no matter the ordering of the node, the computed eigenvalues will be the same. And it's also computed by the SVD, which then approximates the low-rank approximation of your Laplacian. And these would map to the singular values in if the graph is asymmetric. Okay. So here, just as one concrete example, so in terms of how the Laplacian eigenvalues and the geometry of the graph are connected, actually from spectral graph theory, we know that for fixed type of graphs, you have well-known behavior of the eigenvalues. So for example, if you have a fully connected graph, then you have one connected component, which means the first eigenvalue, like by first, I mean the smallest one, will be 0. And then everybody else will be of n. So n is the number of nodes that you have. So that means that all the nodes have the same connectivity. So you can intuitively see the graph geometry in this case from the Laplacian eigenvalues alone. And then if you have a star graph, which is what we see from the right, then you can see that besides the central node, which is connected to everybody in the star graph, all the other nodes have only one edge. So the actual eigenvalues of the star graph will actually have 1, 0, which is one connected component, and then a bunch of ones, which represent the nodes that have one edge, and then one n, which is the hub node or the central node in the star graph. And then you also have the cycle graph and the path graph. And you can find more from the spectral graph theory textbook by Daniel Spellman if you're interested. And then in terms of performance, in the paper we show that LAD is able to beat the previous state-of-the-art methods, including the edge monitoring, the activity vector, as well as tensor splat. And we show that on a bunch of synthetic settings. So I won't go into detail now because I will have more synthetic experiments in the next paper that are very similar. But for the LAD paper, I will focus on the real-world network and what kind of anomaly we can detect. So, so for the first example, we see the UCI message network, where the node are the students and the edges are the message they send between the students. And the network is tracked over a period of roughly 6 months. And the anomalies are detected as follows. So we detect both the day 65, which is the end of the spring term in a university, as well as the day 157, which is the start of the fall term in the university. So these are 2 example anomalies that were detected. Now there are still other anomalies in the graph, and they could be corresponding to different graph behaviors. But these 2 are the ones that we know for sure that will signal changes in the graph distribution. And then we also have the US Senate co-sponsorship network, which here we see that now the top is the anomaly score plot. So that's the final output of the LAD. So you can see that the higher the anomaly score means that the more anomalous this point is, and vice versa. And the bottom that I plot here are the spectrogram of the eigenvalues. So we can see that at both 100 and 104, the eigenvalues also undergoes significant changes, and they are reflected in the anomaly scores. So in this network, the nodes are the US legislator or the senates, and the edge are the co-sponsorship of a bill. And then the 2 anomalies that are detected are the 100th like US Congress and 104th Congress, which in the first one that says there are significant collaboration between the parties, and then in the second one there is a Republican revolution. For more details, you can find in the political science literature as well. And then we'll go back to the Canadian bill voting network that we see as an example from earlier. So in this case, the 2 anomalies are the 2013 and 2015, which happens to correspond to like the year that Justin Trudeau is elected as the Liberal Party leader in 2013, as well as the Canadian election in 2015. So you can sense the change in the political environment from the temporal graph structure, and then they are detected as anomalies by LAD. Okay, so that's the end of the LAD talk. Is there any questions from the audience?
I have just one question. Is there any relation between the data set and whether the short-term or long-term method can better find the anomalous point?
I think the intuition is that the short-term window should focus on more like drastic changes in the short term. So like they will be more focusing on the events, because the events are more like abrupt changes. And the long-term window would more reflect the change points, which are the changes in the graph generative process. So that's the intuition. But yes, this can vary depending on the data set and the task as well. Yeah, thanks for the question, Farma. Okay, so feel free to type a question in the chat as well. So for the main paper of today, I'll be talking about fast and attributed change detection on dynamic graphs with density of states. This is a joint work with Jacob and my supervisors Guillaume and Rehane. And in this work, we look at the limitations of the existing method. And the main contribution of this work is try to scale up the change point detection method of LAT into millions of nodes and edges and the large graphs. And we see that there's a bunch of limitations in the existing literature. So for example, many of the methods are limited to temporal graphs with only hundreds of nodes. And then all the methods ignores node attributes. So they only focus on the graph structure and do not look into the node features and so on. And some of methods only detect just events or change points. However, in practice, you want to be able to detect both because you do not know beforehand if you will detect an event or change point. And then lastly, one very important part for dynamic graph is that some of these methods cannot adapt to newly added nodes. So if your graph sizes are increasing or shrinking, then these methods will have difficulty. Okay, and then in this work, we propose scalable change point detection, which is the only method that can satisfy like all these properties. Okay. Now, so we have the like the same challenges as before. So the first thing is we still want to compare graphs across time. And in this work, we propose to, instead of computing the exact eigenvalue, we will use density of states. And in terms of scalability, what we want ideally is an algorithm that are linear to the number of edges that you have, so it can scale to as large graph as you have. And the main limitation of LAT from before is the computational complexity. So because we were computing the exact singular values, this can be very expensive on large graphs to O of the n cube. So the solution is density of states. So the density of states method was proposed in a prior paper in KDD 2019, where they focused on the computational and the approximation of density of states. Here, I will give an intuition about like how it works. So in density of states, this is a concept taken from quantum physics, where you will look at the state of the electrons and you will count how many electrons are at what state. So when you bring this over to networks, and specifically the Laplacian spectrum or the eigenvalues of the Laplacian matrix, like what you are focusing on now is that you will first take your Laplacian matrix and all of your eigenvalues. And if you take the normalized Laplacian matrix, all the eigenvalues will be bounded within a fixed interval. More specifically, it's bounded between 0 and 2, where 0 is the smallest one and the 2 are the largest eigenvalues. And then now you have this fixed range, and the density of states are essentially a discretization method, where depending on your choice of hyperparameter, it will divide this fixed range into small fixed size intervals. So for example, you can chop this 0-2 range into 20 fixed size intervals, and then each interval will then contain a variable number of eigenvalues. So in the example that you see on the right, Here's one example of of the density of states applied to the stochastic block model, which is the community structure based random graph model. So here you can see that for each of the being, you would count how many eigenvalues falls within this being. So instead of computing exactly the eigenvalues, you just need to compute how many eigenvalues are within this interval, this small being or the interval. So this allows you to be much faster than actually computing the exact singular values. And actually, you never need to explicitly compute the singular values. So the density of states can be approximated very efficiently using some stochastic methods. So for example, if you want to compute the density of states on the Laplacian spectrum, it would only take the complexity shown here, which is the number of probing vectors times the number of Chebyshev moments times the number of edges you have in this snapshot. So know that both of these, the two prior numbers, are constants. So essentially, you are taking a constant, multiply the number of edges in the graph. So now there's a method that is linear to the number of edges, which can now scale to very large graphs. So this is achieved by using the KPM method, which treats the density of states as a Chebyshev polynomial expansion. And then by sending probing vectors, it can essentially estimates the range of the eigenvalues without having to compute them. So that's the intuition for this method. For the detailed computation, I will refer you to the original paper called Network Density of States. And one other interesting fact that you might want to ask is that, so now we can approximate the eigenvalues. How about the eigenvectors? Because we know that the eigenvectors are very powerful tools and have been used in graph transformers and GNN literature. So can we approximate the eigenvectors efficiently on very large graphs? And the answer is somewhat a yes. So we have the local density of states, which approximates the interactions with the eigenvectors. Note that this never gives you exactly the eigenvectors, and I will talk about the equation in the next slide. And if you want to compute the eigenvectors, then you can use the GQL method, which is in the worst case complexity to the number of nodes squared. However, in practice, this is almost never the case. So this is essentially also a very scalable method in practice. And feel free to stop me here since I will be talking about the math a little bit, if anything is unclear. So in order to compute the density of states, here are what they are in terms of the formulas. So first, you will look at the normalized Laplacian. Here's specifically, we look at these symmetric normalized Laplacian. So you have the Laplacian and that's normalized by the degree. And now you take the normalized Laplacian, which the eigenvalues are now in the range of 0 and 2. Then you can compute the density of states. So the equation of density of states is as I explained, it's essentially computing for this range. So this lambda here, I'm not sure if you can see my cursor. This lambda here is essentially the range of eigenvalue, and you count all the eigenvalues, how many of the eigenvalues are within this range. So that's the direct delta. That's a 0-1 function. If this is in this range, then this is 1. So for each of the range, you would compute how many of that is in the range. So now you have this vector that have the size of the number of beings or the intervals that you have divided the eigenvalue spectrum into. And then for each of the beings, you essentially have an integer counting how many eigenvalues are in that bean. So this is exactly like what we see in the prior plot, where the small numbers that you see here are the number of eigenvalues in that bean. And in order to do the Chebyshev approximation, you need to shift the spectrum by 1. So instead of from 0 to 2, now you have -1 to 1, but they are equivalent. And then the second definition for the local density of states, here we can actually look at the eigenvectors corresponding to the eigenvalues. So this one is a bit trickier to explain, but now the input to the function is which eigenvalue range you are looking at. So the bean that you're looking at, which is the lambda. And then the v is the input vector. So this can be a node attribute. This can be an indicator vector, or just any vector that you have. And the local density of states will compute your input vector v transpose times qi. Qi is the eigenvector corresponding to the eigenvalue in this bean. The eigenvectors corresponding to the eigenvalues in this bean. And then so you are computing a product between your input vector as well as the eigenvector for the specific eigenvalues within this interval. And you are summing over them. So that's why I say that this never exactly like recovers the eigenvector unless you only have one eigenvalue in this bean. So this depends on the distribution of the eigenvalues that you have across multiple beans. And with the local density of states, this enables us to actually look at how does the node attributes that you have on dynamic graphs can interact with the eigenvectors of the graph on a large scale graph. Okay, so here we propose the scalable change point detection called the SCPD method. And the intuition is as follows. So we have the same, yeah, sorry.
Sorry, just one quick question. In the previous slide, we didn't have lambda I and qi exactly, right?
No, so the lambda I and the qi are the ith eigenvalue and the ith eigenvector, but the lambda is the bean that you have.
So I mean, my question is that whether we have the qi or not, because for the lambda I'm almost understand, but I don't understand how we can have the qi and.
So yeah, so the qi is the ith eigenvector corresponding to lambda I, the ith eigenvalue. And the lambda here is actually a it's a real number. So this formulation is when we don't have this small number of beans. Like imagine you have like infinite number of beans. So then you can divide your 0-2 interval into like any number of beans, and then one of the bean will contain exactly one of the eigenvalues.
I see.
So that's how the equation is written, but in practice you would approximate like over beans instead of the exact value. Yeah.
Thank you.
Okay. So going back to the plot here. So on the top, we see the output of the SCPD, which is a time series of anomaly scores. And the higher anomaly scores are detected as the anomalies. Here we are showing one synthetic experiment where the change points corresponding to changes in the stochastic block model, which represents the community structures in the random graph. And in particular, we see that the changes at timestamp 75 means that you are going from having 10 communities into 2 communities. That means the communities have merged. So that's what's being detected at the strip at 76, which is what we visualize here. So So the SCPD method is unsupervised, fast, and scalable. So now you summarize the graph snapshot with density of states instead of the exact eigenvalues. One benefit of that is that because you are no longer taking the entire spectrum as your embedding vector, which think about, you have a like 1 million size graph, you will then have 1 million eigenvalues. So then your graph embedding also gets very, very large. Now with density of states, because now you are discretizing it into multiple beans, the size of the embedding vector is just equal to the number of beans you have. So that will be 20 or 50, depending on independent of the graph size. So you can have a very large graph that are just summarized into a 50-dimensional vector. You also want to compare them across time. So here we use the same pipeline as we see in LAD, where we use the sliding windows. And then again, we use the similarity from the cosine similarity. And we can also incorporate the node attributes with local density of states, which I will show more in the experiments. Okay, any more questions until this point? So, okay, so I will go into the experiments. So we compare with a few baselines. Spotlight, which is a different subgraph anomaly detection method, and then we have edge monitoring, which is a very scalable method, but it usually have poor performance. And then in terms of the graph generators, we are running the SBM model, as I mentioned, as well as the BA model, which is the preferential attachment model. So first, I will get started on the plot that we see before. So here, this is the standard evaluation setting for change by detection in temporal graphs, where we are looking at the SBM model, and then the changes that we planted have both events and change points. So the events are just increased cross-community connectivity. So we see like a lot of cross-community edges, and then the change points are the number of communities that would change, as we see before. And a very quick plot about the scalability of SCPD. So we can see that SCPD can scale close to linearly with the number of edges. So for example, the computational times in seconds are only a few hundred seconds when you go to like 30 and 40 million edges in the graph. And it scales similarly as Spotlight, which is a subgraph tracking. And the n-cube complexity of LAD will essentially make it intractable on very large dynamic graphs. And the edge monitoring method scales very well, but it doesn't perform well in practice. And then here are some performance overview. I will go through the different experiments in detail next, but essentially, by using the density of states, we can achieve the same performance as LAD while being much faster and much more scalable. Okay, so in this experiment, what I call the evolving size experiment, where we have a dynamic graph that grows over time. So again, we're using the SBM model, but the number of communities would increase, like the number of nodes would increase, and the nodes would form new communities. So for example, if you go from 16 to 31, you're adding one more community of 300 nodes. Yeah, and we have these changes. Like we also have the number of communities being like expanding and shrinking and so on. And we can see that SCPD is able to detect all the anomalies. And though I think one interesting future work is to see how are the spectrum actually reacting to all these changes. You can visually see like all the change points in the plot, but it's not like very well understood of the Laplacian spectrum on real world graphs, because it's very hard to derive theoretical guarantees. And then here is on the BA model, or the preferential attachment model. So here the change in the parameter is just the increasing density of the graph. So by changing the parameter m, we're attaching more edges when a new node arrives in the BA model. So the graph essentially gets denser over time, and you can see this very interesting change in the spectrum. So when you have m equals to 1, the graph is disconnected. When you go to m equals to 2, the graph is connected. You can see that at the point 16, the changes are very drastic, and then the spectrum start to kind of narrow into the middle part as the graph gets denser. And then the graph gets closer and closer to a fully connected graph later on. And here I will talk about the real world experiments. So first we have the MAG history. This is the Microsoft academic graph. And then here we take the papers that are published in the history field. And then the notes are the authors in this, the notes are the authors of the papers. And then the edges are the co-authorship. So here we have around 0.7 million nodes and around 2.8 million edges across close to 200 years, from 1837 to 2018. And I'm able to run this about 30 seconds on my laptop CPU. Note that SCPD doesn't actually use the GPU and can run really fast on just standard CPUs. The change points that we have detected are very interesting. So we can see that the different international wars can actually correspond to the change in collaboration pattern in the history community. And we believe that this is because, for political reasons, obviously, that the publication patterns will change around these international wars, and probably the views on the history will also change as well. So like we detected the Second World War, as well as the American Civil War, and so on. For the next network that we look at is the COVID flight network. So this is a crowdsourced flight network of the different airports and flights between them in the world at 2020, which is when COVID happens. So we have a lot of distribution change in 2020 because of the flight restrictions. So here, by using the global density of states, we can find the global graph structural changes. So we see that SCPD detects the travel ban from US to EU, and these are huge disruptions in the network, because the US flights accounts for more than 25% of all the flights in the world. And the snapshots are weekly, and the nodes are the airports, and the edges are the flights. And you can also see the change from the spectrum. And here is one example of the attribute change. So I talk about the local density of states. It can take an input vector, and in this case, we set it to be the node attribute. So the node attribute is an indicator vector showing if a particular airports are located in China or not. So by zooming into these specific nodes, we can look at how does the attribute interact with the graph eigenvectors. And we see that the change points that we detect here are way earlier than the global change points. So the change points for the Chinese airports is actually happening around the end of January and the beginning of February, which is when the US first bans flights from China. So this shows that by looking at particular node attributes, you are able to find particular local changes in the graph. And lastly, recently we have added one more experiment where we look at the stable-coin transaction network, which actually the authors of the dataset paper of the stable-coin transaction network will actually be presenting at the Temporal Graph Reading Group next week. But here I have applied SCPD on this large transaction networks, where the nodes are the IP addresses and the edges are the transaction between these nodes. And what's very interesting is that SCPD is able to clearly detect. So the first largest peak is on the 4th of May, which is 3 days before the Terra Luna crash. And according to reports, this is when there start to be like illegal activity on the stablecoin network that would lead to the Terra Luna crash on the May 7th. And then there's also another huge peak on the 26th of September, where more types of blockchain coins are being introduced to the network. So that causes a significant structural change as well. And for the conclusion, for the different properties of the SCPD, it is very fast and only requires CPU. So, if you are exploring some temporal graph data set, I will recommend to try it out and see what kind of results you can get. This is also very scalable. So this can very easily scale to millions of edges and nodes. And we show that it has good performance on real-world data set and synthetic data sets. And you can also use the node attributes to get more insight from the temporal graph. And the code and data set is available here. The code repo is at this GitHub link. And I will be sharing the slides after the talk as well. And yeah, thank you for listening. And well, the dog on the left is our family dog. Yeah, so I have some link to the TG Reading Group here, as well as to my personal website. In terms of future work, so I have actually also worked on extending that to the multi-view graphs. So the archive preprint is available on my website, but it is currently under review. And then one direction that I think is very interesting is how to explain the change points. So both the output of LAT and SCPD can only tell you where the distribution change happens, but it doesn't tell you exactly what happened. So I think it will be very interesting to have more explainability-based method for that. And then also, how can we have a temporal graph GNN that can adapt to changing distributions, especially when you want it to run for long periods of time. And I will go back to the slide with the dog photo for the links. Is there any question from the audience? That's the end of my presentation.
Hello, Andy. Could you hear
Hello?
me? Yeah,
yes, I can hear you. Yeah.
Great. I think this speech is very, very interesting. I have several questions. The first is quite simple because I don't see all the details. Just how to calculate the anomaly score.
The anomaly score is y minus the cosine similarity. So it is just computed from cosine similarity with some post-processing steps.
Okay, okay, great. And
Yeah.
I have seen that you mentioned that there are lots of you focus on some changes like the number, like the event and change point, right?
Yeah. Yeah.
Uh, because I think that's very nice and very interesting. It shows the patterns that show that
Mhm.
it's really show some interesting for the evolutions of graph. But I want to ask, do you have also tried some other kinds of evolutions besides of? I think perhaps maybe there are some other changes may be interesting for perhaps
Mhm.
for these kind of or other kind of data. Have you tested
Right.
it?
Right. So like for example, like one example would be the attribute change. So that's the local density of states. You can use it to monitor the change in the attribute and then how the attribute interact with the graph structure, right?
Okay.
Um,
Yeah.
so that's local density states. But of course, there can be like other changes, but the events and the change points are like umbrella terms. So like the events can be the attacks on the network, or
Yeah.
or it can be like some dense behavior and so on. And then the change points will just be the distribution shift or the change in the graph global distribution. So you have more communities, or you have more nodes and so on.
Okay, great. And another question is that I have seen that in your article, you normally you propose this SCPD, right?
Yeah.
Yes, you leverage the density of states, the DOS framework
Yes.
to prominently the spectral density. But I have a
Yes.
question is that if in a very special case, that means for example, the density are really extreme, but when you average, it becomes a normal, and you see, and now you have a new window, a new graph that it matches really the average, and then, but it could be an exceptional graph. Can this model treat this kind of cases? Have you ever
Are
considered that?
you saying the two graphs have different sizes, but they have the same density of states?
Yeah. Okay. This,
Is that what you're saying? Is that they have different sizes, but they have the same distribution of the eigenvalue?
okay, but okay. Uh, but if the average of the eigenvalues, for
Yeah.
example, with compared to the average is the same, but for example, your sequence of graphs are very special. That means the the eigenvalue could be very large and very small, very large as the beginning and very small as the last. The
Oh,
average could,
right. That's why we use the normalized Laplacian matrix. So all
okay,
the eigenvalues are bounded in 0, 2.
easier to, yeah. Uh,
So
okay, yeah,
yeah. So here we don't look at the exact magnitude of the eigenvalues. So actually that's one difference between LAT and SCPD, because in LAT we use the unnormalized Laplacian. So the magnitude of the eigenvalues are taken into consideration. But for the SCPD, we look at a normalized one. So you kind of lose some information by doing the normalization as well.
okay,
So
great.
yeah.
And the last question is for your last slide, for your future work. I have seen that is a
Yeah.
multi-view, and could you explain some more for the multi-view graphs?
So for the multi-view graph, essentially, what you want to look at is that you have different temporal graphs that are describing the same underlying network. So for example, in
Okay,
this work, can you still see my screen?
yeah,
Okay. So I don't have time to go into detail for this work today, but for example, I will just show the main visualization here. So like in this case, one of the data set that we look at is the traffic network.
yeah,
So we have different views, And then these are like different taxi companies, and they have like the nodes are a different district, and the edges are the traffic of these different companies. So you have like the for hire like vehicles such as like Lyft and Uber, and then you have the taxi companies, but they are all describing the same underlying New York traffic network. So then you can look at their data all together, and then you can draw stronger conclusions. So that's what I mean by the multi-view dynamic graph.
Ah, great. Okay. Okay. Thank you very much. It's
Yeah,
very clear.
I'm happy to discuss more. Yeah, or like
Yeah.
offline as well. Yeah. Thank
Great,
you.
great. Thank you.
Yeah. Thanks for listening. Is there any other questions from the audience? Okay. I think we are also at time. But Farma, do you have a question?
No, actually, I just wanted to mention if there's no question, we should probably wrap up.
Yeah, we can wrap up now.
Yeah.
And thanks everyone for joining the talk today. And feel free to ask me any question on the Slack or send me by email. I'm happy to answer any clarification questions. And then all the code is available as well as data set. So I'm happy to help on that perspective as well. Thanks everyone.
Thank you, Andy, for sharing the work. It was very interesting. Thanks, everyone.
Thank you very much. Thanks everyone.
Thank you.
Thank you, Andy.
Thank you.
Thank you.
Bye.
Thank you.
Bye.